Discussing the naming of stereoisomers. As we said, if we have two stereocenters, we must find the configuration of both stereocenters in order to name a compound properly. The configuration of the stereocenters is written at the beginning of the molecule, and it consists of identifying the carbon number at which the asymmetric center is located, followed by the configuration S or R at that carbon. We can then complete the name in the normal process by listing the substituents, the number of the substituent, the carbon number of the substituent followed by the prefix indicating what the substituent is, and the main name of the compound with the functional group of any of the main functional group or suffix of the compound being listed in number before the prefix indicating carbon number in chain, but in this case, followed by the suffix indicating priority group, in this case, all. If we have a Fisher projection, we can still name the molecule. You can find the carbon chain by the longest chain of carbons. In a Fisher projection, the longest chain of carbons is usually down the central line. That's simply the convention for writing Fisher projections. Although, to make it more challenging, some of the tests have stopped using convention. So we would say that the top carbon is carbon 1 in the chain, carbon 2 in the chain is at the first asymmetric center, carbon 3 in the chain is the second asymmetric center, and then carbon 4 in the chain is the last methyl group. They've shown us that the configuration of the asymmetric center at carbon 2 is S. We know from the name that the asymmetric center at carbon 4 should be R. We can confirm this. Bromine is 1. The asymmetric center at carbon 2 is the second group when we're determining the configuration center of the center at carbon 3. Methyl is 3 and hydrogen is 4. If we draw our lines going from 1 to 2, you can already tell that this is going counterclockwise. When we go counterclockwise with hydrogen on a vertical wedge, the asymmetric center is R. I said vertical and I meant horizontal. When we go counterclockwise with the lowest priority group on a horizontal bar of a Fisher projection, the configuration is R for counterclockwise and horizontal. So that confirms that the molecule in the Fisher projection has the name 2S, 3R, 3-bromo-2-butanol. Naming stereoisomers. Again, if you can take one stereoisomer and identify the configuration at each carbon, when you have the diastereomers, you can already know what the configuration of the carbon is for each of the diastereomers. The names of diastereomers will only differ by the designation of the configuration at the two asymmetric centers. So if we look at our 4 stereoisomers for 3-bromo-2-butanol, you can see that the only difference in name is the configuration. 2S, 3R, 3-bromobutanol. It's an enantiomer, 2R, 3S, 3-bromobutanol. The diastereomer of the first pairs, 2S, 3S, 3-bromobutanol. Even looking at the name, you can tell that it is a diastereomer. One asymmetric center stays the same. Two S. One asymmetric center changes. 3R is not the same as 3S. Then we have the enantiomer of the 2s3r. So we'll make 2r orange. 3r is blue, is green, 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 green. And the designation 3s can be red. So the stereoisomer at the very right is the enantiomer of the 2r3s. Both of the asymmetric centers change. 2s is not equal to 2r, 3r is not equal to 2s. But the asymmetric center at the left is the diastereomer of both molecules, the last two molecules in line, because for the third in the row, 2s is equal to 2s. So one stereocenter stays the same, but 3r is not equal to 3s, so one changes. That's the definition of a diastereomer. It's also a diastereomer of the molecule at the left is also the diastereomer of the molecule at the very right. While the 2s is not equal to 2r, one center is different, the 3r is equal to 3r. So one is the same. One is different, one is the same. That is a diastereomer. It's very important to be able to make these designations. It's very common to ask, what is the relationship between molecules on an exam? We like to give you two molecules and not tell you the relationship, and then have in multiple choice, are these diastereomers, enantiomers, meso compounds, or another term, such as constitutional isomers. Let's look at some physical properties of stereoisomers. Tartaric acid has only 3 stereoisomers because it has a meso compound. There are 4 identical groups bonded to the asymmetric center. The groups bonded to the asymmetric center at 2 are equal to the groups bonded to the asymmetric center at 3. And so we know that a meso compound will result. We can look at the physical properties. The meso compound is the diastereomer of the 2r3r tartaric acid and the 2s3s tartaric acid. The 2r and the 3r has a melting point of 171. Its enantiomer, 2s3s, also has a melting point of 171. Remember that the only property that differs is the direction in which it rotates light. So the specific rotation has an equal value but opposite sign. The 2r3r rotates light to clockwise at 11.98, and the 2s3s rotates light counterclockwise at the value of 11.98. The solubility of the two molecules is the same. For the diastereomer, the melting point is different. It has only a melting point of only 146 compared to the melting point of the tartaric acid at 171. Of the other of its diastereomers, the enantiomer pair, 171. The specific rotation of the meso compound is 0. Because it is meso, that means it has a superimposable mirror image and does not rotate plane polarized light. The solubility is also different. Instead of 139, it is 125. Finally, we look at a 50-50 mixture indicated by plus minus of tartaric acid. What this is taking is making a solution that is 50% 2r3r and 50% 2s3s tartaric acid. We know this from the symbol given in front. This symbol given in front of plus minus indicates a 50-50 mixture that is called racemic. A 50-50 mixture of 2R, 3R, and 2S3S tartaric acid will have a different melting point, and the specific rotation will be 0. Because we have equal amounts of substance that rotates light in the positive direction and an equal amount of substance that rotates light in the negative direction, the overall is to cancel out the values. Positive 11.98 minus 3.98 is equal to 0. The solubility, however, of the racemic mixture will be the same as the pure enantiomer.